Imagine a rushing river suddenly branching out into 3 separate streams. The water doesn't stop, it just divides its total volume across the available routes. Electrical current behaves exactly the same way when we wire components in a parallel circuit. A parallel circuit is defined entirely by its physical layout. Multiple components connected across the exact same 2 electrical nodes. For ITI students, the formal definition is clear. Ecatic electrical component eki duiti pointen mote connected. Multiple electrical components connected between the same 2 points. By anchoring every component to these 2 common points, we physically construct multiple independent paths for the current to travel. In a basic series loop, electrons have only one highway. Here, the electron flow hits a junction and has a choice of routes. This multi-path architecture dictates 3 rigid rules for how voltage, current, and resistance behave within the system. Mastering a parallel circuit requires looking past the physical shapes on a diagram to understand how dividing a pathway alters the behavior of electricity itself. The first rule governs voltage. Because every single branch in the circuit is anchored to the exact same origin node and the exact same return node, the electrical pressure across them must be identical. Looking at this schematic of a 3-branch circuit, if we probe the top and bottom nodes of each separate branch, the readouts match exactly. The total voltage equals the voltage at branch 1, branch 2, and branch 3. The pressure is uniform. The second rule governs current, which behaves entirely differently. While the pressure stays constant, the actual physical flow of electrons fractures when it hits that common entry node. You can see the total current leave the source, hit the junction, and split down the 3 branches based on the path of least resistance, before recombining at the bottom. This means the total current of the entire system is simply the sum of the individual currents flowing through each of these separate branches. Written formally, I total equals I1 plus I2 plus I3. The shared anchor points physically lock the voltage in place, while the separate physical branches divide the total current flow. The third rule governs equivalent resistance, and it involves a mathematical paradox. Adding more resistors into a parallel circuit actually decreases the total resistance of the entire system. This happens because every new parallel branch creates an additional physical path for the electrons, making it easier for the overall current to flow through the circuit. For systems with 3 or more resistors, we use this standard fractional formula. We add the reciprocals of each branch to find the total, but field electricians frequently deal with just 2 parallel loads. For that, we use this faster shortcut. R total equals R1 times R2 divided by R1 plus R2. We can validate this shortcut by calculating the total resistance of a circuit containing a 10 ohm and a 20 ohm resistor. First, we multiply the values for our numerator, 10 times 20. Then we add the exact same values for our denominator, 10 plus 20. This simplifies cleanly to 200 divided by 30, which gives us a total equivalent resistance of 6.67 ohms. Notice the mathematical outcome. 6.67 ohms is less than 10 ohms. The total resistance of the circuit is lower than the value of the smallest individual resistor inside it. Giving electrical current multiple options to travel physically reduces the system's overall opposition to that flow. This abstract math dictates the practical reality of every building you walk into. Every standard household load is strictly wired in a parallel configuration. Power enters the home from the main supply line and hits the distribution board. From there, it splits into independent parallel branches for specific loads: a light, a ceiling fan, and a wall socket. Consider a common scenario. A single light bulb burns out, destroying its internal filament. The physical pathway in that top branch breaks. The circuit for the light is open. But because the fan and the socket are on independent branches connected to the main supply nodes, current continues flowing to them without interruption. The independent paths and the uniform voltage of the parallel topology prevent a single failure point from shutting down the rest of the house. This structural fault isolation is why parallel wiring is the absolute standard for domestic engineering. Before taking the exam or stepping onto a job site, you need to be able to distinguish between circuit topologies instantly. Here's the core dichotomy. Series circuits run on a single loop, while parallel circuits split into multiple branches. For series, memorize this. The single loop means you have the same current everywhere. For parallel, the shared nodes mean you have the same voltage everywhere. Let's test this logic against standard electrician interview questions. First, what defines a parallel circuit and what happens to the voltage? The defining feature is multiple paths for current, and because of those paths sharing nodes, voltage remains identical across every branch. Next question, how does current behave and where is this topology primarily used? Current divides across the separate branches. It creates independent physical paths, making it standard for house wiring. Finally, looking at this multiple choice question, a 10 ohm and a 20 ohm resistance are connected in parallel. What is the total resistance? As we proved earlier using the product over sum formula, the answer is D, 6.67 ohms. In our next lesson, we will apply these topological rules to standard electrical symbols, mapping out specific components like fuses, MCBs, and transformers. Electricians who can solve for equivalent resistance gain the ability to predict system behavior before a breaker is ever flipped. This mathematical clarity distinguishes a skilled troubleshooter from a basic installer.